Hello everyone, I am Tushar. Today we are going to talk about code conversion, especially binary to Excess-2 converter. So let's see what code conversion is and binary to Excess-2 converter is. So uh, let's see what's code conversion actually. Yeah, code conversion is a digital design. In digital design refers to the process of converting one digital code representation to another. So if like in any of the like boolean functions or like in the uh, logical circuits, if you're having like here one circuit and here one more circuit, like if the circuit A is using the same code but in the format, let me say format 1, and if the circuit 2 is using the same code but in format 2, like both are representing the same codes but in a different form, like uh, they are like with respect to with their own scopes. So that is what the code conversion, like that is where we are using the code conversion. So we are having like many different types of code conversions. We are having BCD conversion, where BCD refers to the binary coded decimal. So we are having the decimal numbers 0 to 9, right? The decimal system is having values from 0 to 9, and this one 0 to 9 can be represented in the binary in the form of like 4-bit binary. So 4-bit can have the numbers from 0 to 15, but as we are having the decimal 0 to 9, so we can use from 0 to 9, and the rest of them we can make them as don't care. So and then we are having BCD to Excess-3 code conversion, BCD to Excess-2 code conversion. So in this lecture, we are gonna talk about Excess-2 conversion in detail. So now we are having Excess-2 conversion here. So let's see what Excess-2 conversion is. So Excess-2 is a binary coded decimal code where each decimal digit is represented by adding 2, that is decimal 2, to its corresponding 4-bit binary representation. And then we are having the reversal of that one, that is Excess-2 to binary representation. So there will be having the number that is already being represented in the Excess-2 format, and to that one we can for like we can convert that into a binary representation. But in this lecture, let us deal with the binary to Excess-2 code conversion. So let's see what's actually Excess-2 conversion is. So let us consider a 4-bit number, that is 0100. This is in decimal, it's 4, right? So if we are adding decimal 2, that is 0010, to this number, then what we'll be getting? So 0100 is decimal 4, 0010 is decimal 2. Then if we add them together, what we will be getting is the 6, right? So let us see the binary addition here. This is the least significant bit and is the most significant bit in this binary number, and here also the same. So the index values we can take from 0 to n minus 1, that is this is the 0th index, first index, second index, and third index. So let us add both the binary numbers, that is from right to the left. Let us if we say like the 0th bit is having here like 0, and here 0, 0 plus 0, the sum is 0, then the carry to the next bit is also 0. Then we're having in the first bits like 1 and 0. If we add 1 and 0, we will be getting sum as 1. The carry that we got from the previous bit is 0, so 1 plus 0 is 1, the sum is 1. The carry that is forwarded to the next bit is 0. Then we are having in the second bit 0, and here 1. 1 and 1 plus 0 will be giving us 1. Then the carry that we got is 0. So 0 plus 1 remains the same, that is 1 as a sum. Then the carry that is being forwarded is 0. Then that carry is added to the sum of these two, uh, that is the last bits, that is 0 plus 0 is 0. Then the carry that we got is 0. 0 plus 0 is 0. Then the carry that is being forwarded is also 0. So what we got is 0 1 0 0. So 0 1 0 0 is the binary representation of 6. So what's actually Excess-2? So we are having a 4-bit number, then we are adding the decimal 2 decimal 2, that is 0010 to it. So then whatever the number we will be getting now, so that is called as Excess-2. So here we are having the decimal 4. After that one we are adding decimal 2, that one, then we will be getting decimal 6, that is 4 plus 2 is 6. So let us see in detail for the 4-bit representation. So if you are having the 4 bits as input, so the total number of combinations are like 16. That is 2 power 4. We are having the A, B, C, D as the 4 inputs. So 2 power 4, that is 16. There are 16 combinations for the inputs, and after applying the Excess-2 code, we will be getting the 4 corresponding outputs. Let us see one by one. So we are having the 0, 0, 0, 0. This is 0, that is a decimal 0. After after doing Excess-2, that is adding decimal 2. So 0 plus 2 will be in this decimal 2, that is 0, 0, 1, 0 is a binary representation. Then I am having 0, 0, 0, 1. This is decimal 1, to which if I add decimal 2, that is Excess-2 code will be 0, 0, 1, 1. That is nothing but decimal 3. Then I'm having 0, 0, 1, 0. This is the decimal value. This is a binary representation equal to decimal 2. Then if I add the decimal 2, then I'll be getting the decimal 4, that is nothing but 0, 1, 0, 0. Then I'm having 0, 0, 1, 0, to which if I add 2, then I will be getting 0, 1, 0, 1. That is 3 plus 2 will be giving me 5. Then I am having the decimal 4, that is 0, 1, 0, 0. If I add 2, I will be getting decimal 6, that is 0, 1, 1, 0. Then I am having 0, 1, 0, 1. After adding 2, I will be getting 0, 1, 1, 1. Then again I am having 0, 1, 1, 0, to which if I add 2, I will be getting 1, 0, 0, 0. Then I'm having input as 0, 1, 1, 1. Then the output is 1, 0, 0, 1. So let us see the other 8 combinations too. So 1, 0, 0, 0 is my input, and then if I add decimal 2 to it, this is nothing but 8. So 8 plus 2 is 10, that is 1, 0, 1, 0. Then I'm having 9 here. 9 plus 2 gives me 11, that is 1, 0, 1, 1. The binary representation of 9. After having the this is what the after adding decimal 2, I'll be getting the Excess-2 as 1, 0, 1, 1. Then I'm having 1, 0, 1, 0. Then decimal 2, if I add 1, 1, 0, 0 is the output. Then I'm having 1, 0, 1, 1. Then the output is 1, 1, 0, 1. Then I'm having 1, 1, 0, 0 as the input. Then corresponding output is 1, 1, 1, 0. Then I'm having 1, 1, 0, 1, to which 1, 1, 1, 1 is the output. So this is uh, it's like this 2 power 3, that is 8. Then 2 power 2, that is 4. 8 plus 4 is 12. 12 plus 2 power 0 is 15. So sorry, 12 plus 1 is 13, right? So for the 13 in the decimal representation, for the decimal value 13, after the uh, Excess-2, that is after adding decimal 2 value, I'll be getting the decimal 15. That's what the maximum limit I can push into a 4-bit number, right? So if even though if I'm having like 2 more combinations, that is 14 and 15 as the inputs, still I am not getting the output. Why? Because in 4-bit we can't represent the decimal number that is more than 15. So I'll be considering these two as don't care, that is represented by X. So don't care refers to a condition like whether the X can have the value 0 or 1. So let us see how these uh, outputs X, Y, Z and W depends on the input. So for that one, uh, we want to have the min-term representation. So what do you mean by min-term, right? So a min-term is a specific product term that represents a unique combination of inputs for a given Boolean function. So in the min-term, so previously we had for W, uh, if the output is like 1, 1, 1, like wherever the output is 1, we are taking that min-term number. Actually the min for the 4-bit uh, input, we are having the min-terms from M0 to M15. So for W at the position 6, 7, 8, 9, 10, 11, 12 and 13, we are having the output as 1. So those terms are considered as the required min-terms, and anyhow 14 and 15 are considered as don't care conditions. So like as I told, don't care refers to either the value X can take 0 or 1. So we are like including them here. This sigma represents that this is the min-term combination. Min-term refers to sum of products where each of these terms are each of these terms are being written in the form of product, right? So all those product terms are being summed up together. So in the similar way, we are having X as a sigma M of 2, 3, 4, 5, 10, 11, 12, 13 plus the don't care condition for 14 and 15 positions. Then I'm having Y as a sigma of min terms of 0, 1, 4, 5, 8, 9, 12, 13 and then the don't care conditions for 14 and 15. Then Z is having sigma M of 1, 3, 5, 7, 9, 11, 13 and then similarly don't care condition for 14 and 15 for all the four equations. So let us see the way to simplify these four Boolean expressions using the K-map. So the K-map is a graphical representation used for simplifying the Boolean expression. So in the other way, we can use our Boolean theorems and postulates to simplify them. But I think the easier way is to use a K-map, where we can have like a circle we can have which is having a single element. So then we can have a pair which is a combination of like two elements. Then we can have the quad which is a combination of four elements. Then we can have the combination of eight elements that is called as oct. So let us see how we can have the K-map for all these four uh, outputs, that is W, X, Y and Z. So let us see one by one. So for the K-map for the output W, that's like what we got as sigma M of 6, 7, 8, 9, 10, 11, 12, 13 plus the don't care condition for 14 and 15. Using these min terms and the don't care, we are having the K-map. So K-map uses the gray code. Like gray code for the 4-bit representation, we are having like A bar, B bar. So in min terms, as we know, bar is representing the zero value. The binary value 0 is being represented by the bar term, and then a normal value as we are having here A and B represents the 1. The gray code says that these two adjacent or these two consecutive terms, the difference between these two consecutive terms has to be 1. So these two are 0 0 in terms of binary, 0 0 0 1. So if I take A B bar is 0 1. The difference between these two will be how much? 2. So that can't happen in terms of gray code. So we are having A bar B bar, that is 0 0, then A bar B, that is 0 1, then A B, that is 1 1, then A B bar, that is 1 0. So between these consecutive elements, we are having the difference to be 1. Similarly here too. So then the values, these min terms are like encoded here like in a special format. Like this first box is the min term for 0 0 1 2 3 4 5 6 7. Then 8 doesn't come here. 8 will be in the A B bar line. Here 8 9 10 11. Then here 12 13 14 and 15. So here we are having the, for this one, W equal to sigma M of for the min terms 6, 7, 8, 9, 10, 11, 12, 13. So 6 starts from here, right? So 6, 7 are 1, then 8, 9, 10, 11 are 1, then 12 and 13 are 1, and then I'm having the 14 and 15 as the don't care conditions, where I can represent them as X and X here. So X can be considered as 1, like if there is any possibility of having a combination of like maximum number of elements, I can enclose even these don't care conditions within them. So, so here in both the rows A B and A B bar, I am having 1 1 1 1 1 1 here. If these two X are all X togetherly can form, all these 8 can form a oct, right? So all these 8 togetherly forms a group of oct, which can be simplified to A. It's like in these two rows, the common term is A, and all these things put together will be giving me the output as 1. That is C bar D bar plus C bar D plus CD plus C D bar. So all these things togetherly will be giving me the output as 1. 1 and the common term within this common in general refers to AB plus AB bar. If we take A as common, then what remains inside is B plus B bar. So B plus B bar reduces to 1, then A into 1 is 1. This A into here what we got as 1, A into 1 is A. This is what the group 2 have represented as. Then the one more thing is 1 1 X X. Here even I can have a pair, but including these two don't care conditions, I can have the maximum number of elements of 4 elements. That can be like quad. So these four things put together can have a group of BC. So in these two rows, I'm having the common term as B, and in these two rows, I'm having common term as C. These two B into C, that is B and C put together will be giving B and C. So the Boolean expression for this W is group 1 plus group 2 or group 2 plus group 1. Anyhow, like the addition is commutative. So A plus BC is the Boolean expression for W. Similarly, let us see for X. So for X, I'm having the minterm representation as 2, 3, 4, 5, 10, 11, 12, 13, along with the don't care conditions for 14 and 15. I'm having here, I'm just like representing the box means the same, the K map box means the same in all the things, like even W, X, Y, and Z all are like 4 bits, right? So they means the same. So 2, 3, 4, 5. Then I'm having here uh, 10, 11, 12, and 13 here. So these four put together can form a quad. So these two put together, the common things in these two is B, and in these two is C bar. So B C bar is a group one, and here also one more group. There is nothing like we can have a group like this or like this, like within the same thing. They can like overlap. If like they are making a circular shape, let us think as a circle. So we can have the in the other form too, like these two A B bar as a one row and A bar B bar as a one more row. These two put together also forms one more quad that will be giving us B bar C. So in this one and this one, the row 1 and the row 4, the common term is B bar, and in these two the common term is C, that is B bar C, and the one more group is B C bar, which I have already computed. These two put together will be giving the Boolean expression for X, that is B C bar plus B bar C. Now let us see for Y. So Y is represented as a combination of min terms of 0, 1, 4, 5, 8, 9, 12, 13, along with don't care for 14 and 15. These are represented like 0, 1, 4, 5, 8, 9, 12, 13, along with the don't care for these two. That is 14 and 15. So these all these things put together can form a octet. That is, octal combination can be formed. So in these two, the common term is C bar, and then all these things put together will be giving me 1. So like there is no need to include X here. Like there is no need for us to have these things. So these are considered to be a 0 in this particular condition. So Y will be giving me C bar. So then we are having Z. Z is sigma m of 1, 3, 5, 7, 9, 11, and 13 with don't care for 14 and 15. These are min terms are represented as like 1, 3, 5, 7, and then here 9, 11, and then here 13, along with the don't care for 14 and 15. So these 8 things put together forms an octal combination. So we will be giving me the output as D. The common term is D, and these all these 4 combinations put together will be giving 1. 1 into B, that is 1, and D is D. That is a Boolean expression for Z. So now let us see the circuit, that is Boolean logic circuit for these outputs W, X, Y, and Z with respect to the 4 inputs A, B, C, and D. So the logic diagram for that one, we are having 4 outputs as a combination of inputs: W equal to A plus BC, X equal to BC bar plus B bar C, Y equal to C bar, and Z equal to D. So I'm having the 4 inputs A, B, C, and D, and then I need a NOT gate to represent C bar and B bar, right? So for that one, to represent a B bar, I'm having a NOT gate to which I'm taking the input from B, so the output is B bar, and one more AND gate having the input as C and the output as C bar, and like I'm having the other 2 inputs, that is A and D. So for W, I'm having A plus BC. So BC represents B and C, where like an AND gate has to be there, to which B and C are the inputs. So I'm taking B and then C, and I'm putting an AND gate which will be giving me the output as BC. Along with that one, I'm having A, and A and BC are put together with respect to an OR gate. So this is BC, and then I'm having the A or BC, that is what W is the output, right? So then I'm having one more output X, that is B C bar plus B bar C. This is actually the XOR representation of B C, right? So even I can have the direct XOR representation here, but as I'm using the basic gates, I can use like two AND gates for representing B bar C and B C bar separately, and then taking the output of those two AND gates, and then having an OR gate to get the final output. So I'm having an AND gate here for B C bar, taking the input from B and then from C bar, then one more for B bar C. These the output of these two AND gates are given to an OR gate, and I'm getting the X, and I'm having Y. This is nothing but just C bar. Whatever the output I'm getting from the C bar, that is the NOT gate, upon applying to the C, that is C bar, that is same as the Y, and I'm having Z, that is D. There is no need to do any computations or any logic gates, but if we want to have here, we can have two NOT gates that can be simply represented with the help of a buffer. Two NOT gates, it's like D, after applying a NOT gate, it will be giving me D bar, then D bar, upon applying the NOT gate, will be giving me D again. So there is no need to do all those things. We can just have D here. So this is what the uh, 4-bit binary to Excess-2 converter logic diagram is. So uh, then we are having the applications of this one Excess-2 binary to Excess-2 converter, that is like BCD arithmetic. Excess-2 is often employed in binary coded decimal arithmetic. Adding or subtracting BCD numbers in Excess-2 can simplify the processes. And then in the circuit design also, Excess-2 representation might be used in certain circuit designs or components to facilitate specific operations. And then in the terms of error detection and correction, we are using and then decimal to BCD, as I told you earlier. This is what the application of BCD. Um, I hope you all understood. Keep learning. Thank you.